Good afternoon, everyone. I'm very glad to talk about our new work on a new off-policy policy gradient algorithm. And this work with my advisor, Emma Bronsky, who just gave a great talk, and added Swaminathan and Alec Agua from Microsoft Research. So let's start with why we want an off-policy reinforcement learning algorithm, as Emma motivated that before, and I just want to highlight a few. So first, off-policy algorithm can be more sample efficient as we can share and reuse old data. And more importantly, in many critical applications such as healthcare and some social applications, we require an offline training pipeline where we could not take action in the real environment when we train our algorithm. And in those scenarios, the online on-policy reinforcement learning algorithm can be impractical, and that highlights the need of an algorithm to figure out how to learn good policy using a fixed batch of data collected from a different behavior policy. And we know that policy gradient algorithms, they achieve the state of the art in many tasks. However, most of them require on-policy data. As we show here, we have a table to show whether an algorithm could learn from on-policy data, or both on-policy and off-policy data, or only off-policy data. And it shows that it's particularly challenging for the policy-based algorithm to learn from only off-policy data. And in this paper, we showed a new off-policy policy gradient algorithm, which can learn from a fixed batch of data, which we call OPPG here. And we gave us a theoretical convergence guarantee as well as empirical validation to our new algorithm. So let's recap a little bit about the notations in Markov decision processes. We have state and action, and the policy and state transitions, they are Markovian, as value function is defined as the expected future return of a fixed policy. Once we fix the policy, since the policy and the state transitions, they are Markovian, so we'll have a Markov chain, and under certain assumptions, we'll have the stationary state distribution in this Markov chain. And then, how do we update our policy to maximize the policy value defined as this? The classical policy gradient theorem proposes a way to estimate the gradient of the policy value with respect to the policy parameters here. And notice that here is an expectation taken over a state-dependent distribution, d pi here. Pi is your policy. So it's particularly challenging for off-policy policy gradient algorithm. That is how to estimate this gradient using data from another policy mu. One straightforward way you may think of is just to directly ignore the state distribution difference as here, and the algorithm based on this policy gradient estimates is called off-policy actor critic, and it's the very first practical off-policy policy gradient algorithm, and many state-of-the-art algorithms such as DDPG later built on top of this. But the problem here is because of the state distribution mismatch, this introduced a bias to the policy gradient estimates. And this bias is not controlled by algorithm designer or learner like us, but it's fixed once you fix the data set. So this can lead to an arbitrarily biased gradient and arbitrarily worse convergent algorithm, convergent policy if you learn from this. And that's the reason why an algorithm like a DDPG built on top of this still need on-policy data when they actually doing the policy gradient algorithm. So a straightforward way to adjust for the bias is a method called importance sampling, which means you multiply the likelihood ratio here. It's a likelihood ratio of the row in path to the certain state where you want to estimate the gradient on. And here we have no bias because we multiply by the likelihood ratio and the expectation becomes the same as we computed from the target policy pi. But this likelihood ratio has extremely high variance, and it actually grows exponentially with respect to the length of the row in path. So in this sequential decision setting, this becomes particularly impractical to apply this gradient estimate. And here, we're not totally hopeless, and we propose a new way to estimate the gradient, which we want to still keep a low bias as well as a reasonable variance here. That is doing the importance sampling instead of over the path level. Here we are doing the importance sampling over the state level. It's a likelihood ratio of the state under the stationary distribution. And you can think about this as actually marginalize the previous importance sampling over all the trajectory leading to the same state as, and then the variance can be significantly smaller in this case. But the next problem becomes, first, when this ratio is actually defined, like when d mu, the support set of d mu covers the support set of d pi, and then when we can have an estimator of this. For the second question, actually in the policy evaluation setting, there has been several recent work on how to learn the ratio of the stationary distribution. So basically, they try to fit Bellman-like dynamics like this, and through some algorithm like dynamic programming to solve the ratio W of S. And if we combine this with an off-policy critic algorithm, we will immediately get an actor-critic style of policy gradient algorithm. And here, as we show, we first initialize the policy by behavior cloning to try to use the behavior data more. And then we do like normal actor-critic fashion. And then we are interested in when does this algorithm really work, when can we provide the theoretical justification to this algorithm. The assumption that used by previous work to learn this ratio is actually we need the support set of the behavior policy cover the support set of the target policy we want to evaluate. And this become particularly impractical in the policy optimization case, because here the pi can be any policy in our policy class, and in this case it would be too strong to assume so. And actually we don't really need such a strong assumption, because if we think about policy optimization, all we need is at the end of the day we get a good policy. So we replace this with a milder assumption here, that is the support set of a behavior policy cover at least one optimal policy. And if you want to remove this assumption, it will sort of become information theoretically impossible for you to learn at least one optimal policy, because you cannot you cannot cover the all the possible state action pair with respect to related with the optimal policy in your data, which means there is some important information you missed in your collected data. And so we assume that for any state action pair, we'll visit by at least by a particular optimal policy pi star, it will be visited by our data collection policy. But for any other policy in our policy class, we may not cover them. And then the question is how to compute the correct ratio, the d pi over d mu, or how even we define that. The solution is actually we consider a different MDP. Here we call it behavior constraint MDP, which is for all the state action pairs that will be visited by our behavior policy, we define this as the same as the original MDP. And for all the other actions that won't be taken by the data collection policy, it will lead to a self-loop zero reward state. And in this case, the policy value in this new MDP will lower bound the policy value in the original MDP. And for the optimal policy in our assumption, it will be the same, which means at least one optimal policy is still optimal. And also this MDP has a nice property, that is the trajectory we collect is in the old MDP, and it's very easy to generate the trajectory in the new MDP using the data we collect, because all the additional part in this new MDP is constructed by us, and we know the model and dynamic. We can easily pre-process the data to pretend we actually collect data from this MDP. Then we will talk about a theoretical guarantee we can achieve in this new MDP. That is, under the assumption of coverage, like we mentioned before, and an assumption that the stationary ratio has a consistent estimator, and the critic estimator is also consistent, which is sort of standard. And also, we assume the second moment of d pi over d mu is bounded. And this is also necessary because recently there is a work on minimax lower bound that is actually scale with this second moment. So without a bound on this, we're impossible to learn. So then our algorithm is converged to it's guaranteed to converge to a stationary point of the policy value in this behavior constraint MDP, which means the gradient is 0. And this is actually the first convergence guarantee for off-policy policy gradient algorithm in non-tabular setting. And then we do experiment to test our algorithm in a batch of policy setting, which means we learn from only a fixed data set, and there's no more new on-policy sample collected by the policy during the learning. And the behavior policy actually has very poor performance, which is particularly challenging for policy gradient because we're trying to learn good policy from a bunch of data where the average reward in those data is actually low. And the learning curve, later we'll see, is plotted by testing results, which means it's true result, not just our off-policy estimates. So the first domain we look at is carport, and the x-axis is number of policy gradient step. It's not like a URL experiment. We're not collecting new samples. And the y-axis is the value. Here the behavior policy got a value around 20. And if you do off-policy actor critic without a state distribution correction, it will look like this, get a pretty much improvement over the behavior policy. But if we add the state distribution correction, we get better than off-policy actor critic, and we'll also improve over the gradient step more stably. And the arrow bar here is the standard deviation over different runs of the whole learning process. And here are two more baselines. They were originally proposed in the setting that you reuse off-policy data, but you keep collecting new on-policy data. As we expected here, once we tested them in the batch setting, which means we fixed the data set and no on-policy data, they will perform worse than in the original settings they were proposed for. And this highlights the challenge in the batch setting. And we also tested in a HIV treatment simulator where the state has 6 dimensions and each of them is a number of different cells. And we have 4 actions, measures whether or not taking some drugs. And the transition dynamic is modeled by an ODE system. And here we got even better performance for our algorithm compared with other baselines. And yeah, in summary, we proposed a new off-policy policy gradient algorithm here. And the key difference from previous work is we do the stationary state distribution correction. And we provide the first convergence result of off-policy policy gradient in non-tabular case. And our algorithm outperforms other policy gradient baselines in a batch of policy settings. And there can be potentially some future direction to improve this work, and I'm more than happy to talk with anyone who is interested in. And thank you everyone for the attention.